Hello, today I would like to talk about the school location problem, which is an interesting optimization problem I've been thinking about for a few days. It's sort of a kind of facility location problem. It's also similar to other clustering problems you may have seen before, but it has a very interesting twist that I think makes it very interesting to study. Today I'm going to focus especially on how we can take the mathematical statement of this optimization problem and then express it using JUMP, which is a very powerful language for writing down optimization problems in the Julia programming language, and then passing those optimization problems to whatever your favorite numerical solver is. But first, let's talk about what the actual problem is and what we're looking at here. So I'm going to scroll down a bit and focus just on this picture to begin with. By the way, this Jupyter notebook is free for you to download. I'll put a link in the video description, so you should follow along with that if you're so inclined. The input data is a list like this of points, and you can think of this as a map. So here are the locations of a bunch of families who live in our city. And our goal is to put schools in various neighborhoods in this city. And our goal is in some sense to minimize the distance that everyone has to travel to get to school. So here are the families. Let's say we're building 3 schools, right? If I put a school here, then this person, in order to get to that school, would have this distance to travel, and so on. Now, there are a couple of different ways in which we can understand the distance that a family has to their school, but for now we're going to assume that everyone attends the closest school to them. So what we're going to eventually do is minimize this distance, and then each person is going to the school that's at their minimum distance. So we can see right away that we have a sort of mini-min problem. We're minimizing, in some sense, the minimum of the distances that everyone has available to them. And furthermore, we're going to assume that the distances are Euclidean, but that is something that you can change and explore if you want to use, say, a taxi cab Manhattan distance. That could also be an appropriate choice. The second thing we want to think about then is how do we aggregate these distances over the families. So for example, if I have a school here and this family has to travel that far and this family has to travel that far to school, we could add up their travel times and try to minimize that. That's one natural choice. But instead, I'm going to argue that in this kind of public policy planning arena, a more natural choice is actually to minimize the maximum of whatever these 2 distances are. And the reason for that is this, and I have a paragraph about it here. In this kind of public planning context, one of our very important priorities is to ensure that there's no jealousy, right, among our constituents. So if we try to minimize the average or the total distance that everyone has to travel, then it's possible that in service of the greater good, you're going to end up with one student who has to drive for an hour to school, while everyone else is within 30 minutes, right? However, if we decide to, instead of minimize the average, minimize the maximum distance that anyone has to travel, then we can ensure that there's no single family that has a longer commute than everyone else. And you can do a little proof by contradiction for yourself to see why this is going to be true. And it's not necessarily true if you do the average distance solution instead. Now let's go ahead and take our verbal problem and try to translate it into mathematical notation. So to express the idea that everyone attends the school closest to them, we can go ahead and write the distance between each family and each school as this Q norm here. So that's the distance between these 2, and if we choose the 2 norm, which we will in this demonstration, we're talking about Euclidean distance. You might also choose to use the 1 norm if you live in Manhattan, or whatever your favorite P norm is. And there are n schools. Among those n schools, the school having the shortest distance in this norm is the one that each family is ultimately going to choose, that they're going to attend. So we go ahead and put that family-specific distance in here, and then we're going to take the maximum over all of the m families and treat this as our social cost function. So the longest distance that any family has to their nearest school. And our goal is to minimize that quantity. And as a result, we have this very interesting mini-maxi-min optimization problem. These kinds of mini-max or mini-min problems are common to see in the combinatorial optimization field. But in order to wrangle this into a format that our solvers can interact with, we're going to start by replacing this max expression with a scalar variable t. Now, we'll notice here that this constraint just says that t has to be greater than all of the arguments to the max, right? If you are greater than all of the arguments to a maximum, then you are greater than the maximum itself. And then because this is a minimization problem, we know that this constraint will actually hold with inequality because it can always push t down to be the smallest value that is possible. Unfortunately, that same trick does not work with to get rid of this min here. And instead, we're going to use a kind of binary selector variable. Here, Sij equals 1 if the children of family j attend school I, and it will be 0 otherwise. And now we can write the problem in this new form. And what we've done here is use what's called a big M to kind of build this logic of the minimum into the problem. The easiest way to see why this works is to just imagine if Sij is 0 or 1, what's going to happen. Well, if we look first at this constraint, this says that for every family j, at least one of the SIs has to equal 1. Because this is binary, right? And that just means that every family is going somewhere, right? You can't cheat in the optimization by saying no one goes to school. Once we've done that, then we know that at least one of these Sijs is going to be a 1. And if a 1 occurs here, then that means that this family j is actually attending school I. And this value is going to become 0. And we will correctly have t being greater than this family's distance that they're actually commuting to go to school. Here, m is a very large positive constant. And the reason we make it large is that if Sij is 0, then we're going to subtract a huge number here, and this becomes a trivial constraint, right? You're going to end up with some large negative number over here, and it will not affect the correctness of the solution. So m is going to be a large positive constant. Finally, we have our binary constraint on Sij. Now we are almost ready to start typing in our optimization problem. But there's one change that we have to make in order to solve it efficiently, and that's this. If we look at this first inequality constraint, we can see that we have a linear term on the right, a linear term on the left, but then in the middle we have this norm. Now this is actually a convex function, so from a mathematical standpoint, there's nothing wrong with this. It's still a convex optimization problem if we ignore the integrality constraint. However, it's actually very difficult to differentiate and process this norm function, or at least that's not the most efficient way to do it. And a better way to deal with these is to actually express this as a conic constraint, because we are using a solver called the splitting conic solver that thinks about optimization problems in terms of convex cones. So what I've done here is I've replaced this constraint. I've broken it up into two by introducing the variable dij. What this constraint right here says is that dij has to be greater than the norm of all of the other entries that appear in this vector. In that case, that's xi minus pj. And again, because this is a minimization problem, basically this means that dij is going to equal this norm. And then we just replace the norm here with dij itself down in the previous constraint. And now we have an equivalent program that is formulated in a nice kind of conic way that later on we will see is very easy to notate in our jump optimization language. Now that we have a mathematical statement of our problem, let's try typing it into Julia and see if we can take a look at some solutions. We're going to start by importing a couple of packages. Here you can see we're using the jump modeling language. We have SCS, which is the solver that we'll use to solve the continuous relaxations of these optimization programs. And then Juniper, which is a wrapper that lets us process these integrality constraints. It creates a sort of branch and bound type of scheme. And then we also have a couple of built-in packages that will come in handy. To generate a fake instance, I wrote 20 families and 3 schools here. To make this video go quickly, I'm going to use just 10 families. We're going to have 3 schools, And then n dims here is the number of Euclidean dimensions in which the points are living here. So that's 2 in this case, right? And you can try a higher number, but the plotting code won't work. So 2 is kind of a safe choice. So what we've done here is I started by generating points that were exactly on the unit circle here, and then I just kind of nudged them in one direction. So you end up with sort of an interesting problem with some different kind of neighborhoods in it if you generate random points like this. And now we're going to go ahead and try building the model in the jump language. So I'm going to start by looking down here at choosing the value of m. In general, right, m just needs to be a large constant for the logic of this constraint to work. So if you're like me, you might think, okay, great, I'll just put in 10 billion, right? You can put a very large number in, and that works logically. But the problem is it can create a lot of numerical instability when you pass that down to the solution routine. So to get a stable and accurate solution, you actually want to make m as small as you can without the fundamental logic of this, this constraint breaking. So this requires thinking a bit about the problem. But if we look here, basically all we need is for the right-hand side of this constraint to come out negative when Sij is 0. And in order for this to be negative, we only need to ensure that m is greater than dij, which in turn represents the distance between xi and pj. So what we can do is try to set m to a number that's always going to be greater than the distance between a school and a family. And thinking a little bit more about it, there's no way that an optimal solution is going to have a greater distance between schools and families than the overall kind of diameter of our city, right? So we can think about the diameter of the city as the largest possible distance between any two families, and know that this dij is never going to exceed that in an optimal solution. So that's exactly the value that I chose. I said let's set m to be the largest possible distance between any two families in the input data. It's important that we're using the input data here because we don't know xi, right? We haven't solved the model. Down here, instead of using the 2 norm, I actually put in the 1 norm. The reason for this is that it's a mathematical fact. The 1 norm will be larger than the 2 norm, but setting it this way, it's a conservative choice, but it also will let you use some of the commented out code to try using 1 norm distance instead of 2 norm. The next thing I did, we're kind of moving backwards here, is I set the nonlinear solver to be SCS, as I mentioned above. And then we wrap SCS in this Juniper. So we say we're going to create an optimizer with attributes. And Juniper, one of the options that it accepts is what NL solver do you want to use? Well, the NL solver I want to use is SCS. And there are other options too. You can give it a custom mixed integer program solver. And I've set the tolerance to be somewhat lower than the default because this problem does not require that high of a degree of numerical precision. The next thing we're going to do is put in our variables and constraints. Let me fix that typo for you. And what's really nice about this is that you basically are just typing in the mathematical notation, right? This is very, very similar to what we wrote above, as are these sums, right? The names of the variables, the notation for their dimensions. This is the beauty of the jump language. And the one really special thing that we've used here, the special feature we've used, is this conic constraint here. So you don't have to type the norm of this, right? You just say concatenate d with the vector of x, the points we're working with, and the family's coordinates. And it will automatically process this as the conic constraint that we wrote down up here. So if I run this cell, it's not solving the problem yet, right? This is just constructing the model, and it prints some information about the size of the model, the kinds of variables it has in it, and the number of constraints. And then this cell is the one that actually solves the model. If you have 20 schools, it can take several minutes, but this one I think will only take 4 or 5 seconds. Let's check it out. All right, so it took 5.19 seconds to solve this instance, but what this shows you is that even a relatively simple instance like this, the solution is not printed right away. And this is a very challenging nonlinear integer program, and if you increase the number of families to even 30, this solver can be going for hours and hours. So that just shows the intrinsic difficulty of this kind of problem and perhaps the need for some further investigation into the structure of the optimal solution. So to verify that our solution is correct and to actually obtain the x values from this optimized model, the first thing I do is I grab the value of the x variable. And then in order to make sure that we did this correctly, instead of looking directly at S, I actually wrote some code that checks if these are the school locations, then what is the closest school to each family. And that gives you, right, the index of each school that someone attends. And then I make sure that that agrees with the value of the S variable in our model, as well as that it agrees with the shortest distances as recorded in the D variable. So this is a bit of a sanity check to make sure that we encoded our model correctly. And finally, we can go ahead and plot those original points alongside the optimal solution, and we'll see exactly how it sorted things out. So if we look at the output of our model, we can see that it naturally grouped schools into these sort of neighborhoods. It's not surprising that over here, where there were a bunch of families together, they all end up attending the same school. And then we can also see that in these more spread out areas, it picked a school that was kind of halfway between, right, splitting the distance that these two families would have to commute. Now, when you look at a picture like this, you might think, if you've done some data science coursework or studied in that area before, this is a lot like k-means clustering. K-means clustering is a different optimization problem that arises in statistics. And the goal with that is, given these kind of black squares in a plane, you're trying to find centers so that you categorize each point according to the center that it's closest to, and you minimize the sum of squared distances between each point and the center that it's assigned to. Now the key word there is sum, right? That's equivalent to minimizing the total or the average distance that everyone's commuting, but we rejected that optimization model and decided to minimize the maximum instead. So k-means clustering is fundamentally a different optimization problem, but it can look very similar when you're in this kind of space. And we can think about what the properties of a k-means solution to our problem would be like. Well, the first thing we observe is that because we are minimizing the maximum commuting distance, if I added a new family and they lived way out here in the countryside, then in our model, the best way to minimize the maximum distance would be to take a school and make it kind of halfway between this farmhouse and the downtown area, right? Then this family and these families have the same commuting distance, so it's splitting the difference. And what that says is that our model is not very robust to outliers, right? If you have an outlier way out here, then it can greatly affect the optimal school location plan. However, robustness to outliers may or may not be something that's very important from a public planning standpoint, right? In statistics, we care a lot about robustness, but here we're not dealing with statistics. We're not looking at some sort of random sample or some subset of the student population. We're looking at the actual students, and we're trying to plan for them. So which of these optimization models you choose will depend exactly on the context and whether you view this as a statistical problem or as an operational problem. However, we can also try applying k-means clustering to this exact problem and see if we get anything different. So right here I've used the clustering package in Julia. I've commuted the k-means, and then I've grabbed the x's associated with those k-means. And then I repeat all the same plotting steps from above. I figure out what school everyone's going to, and I generate the same plot. And if we take a look for our same solution here, we get a very kind of different, wow, this is quite striking, right? We have one school that nobody's going to, and these all got assigned to just two neighborhoods. So these got grouped together and those got grouped together. So this is a very different kind of philosophy about how to assign students to schools. And you'll notice that there are a couple of students who are really having to take one for the team, right? This family has a much longer commute, but that enabled the model to have a lower aggregate, a lower sum of distances. And I should mention that this algorithm is not an exact solution for k-means. Confusingly, it's called the k-means algorithm, but it's actually a heuristic for solving that original k-means problem. Well, that concludes this demonstration. Thank you very much for watching. I hope that this was helpful. Most of all, I hope that this inspires you to look more into Julia and the JMP modeling language, which is very powerful and very expressive. I'd be happy to answer any questions that you may post in the comments, and I also encourage you to go check the video description and grab the Jupyter notebook here. Try out this code for yourself, see if you can improve it and solve any larger instances. Thank you so much, and I'll see you next time.